Here is our fourth and final installment of Lesson 3.3, Problem Solving with Systems. This type of problem has to do with rate times time equals distance. It's got a little curveball thrown in. And what this is, like I like to relate it to those moving walkways when you're in an airport. If you get on one of those moving walkways and it's moving at 3 miles per hour and your normal walking speed is 2 miles an hour, you're actually moving at a combined rate of 5 miles per hour. If you're one of those goofballs who turns around and walks the wrong way and you're walking at, I'll have to change it up a little bit, if you're walking or jogging at 4 miles an hour and the walkway is going the opposite direction at 3 miles an hour, you're only moving at 1 mile an hour because you subtract the two because your rate is working against the rate of the moving walkway. And that's how this is going to be with these. We will see these with rivers. Upstream means you're going against the current. So you're going to take your speed of a boat minus the current. And then if you're going downstream, you're moving with the current. So you would take your speed of the speed of your boat plus the current. This works for airplanes with a headwind and a tailwind. Headwind, you're going into the wind, so you would have to subtract the wind speed from your airplane speed. And tailwind, the wind is actually helping you, so you add those things together. So let's get started on this, and we'll talk through how these work out. During rainy season on the Amazon, Pastor Sousa can travel 60 kilometers downstream in the same time that it takes him to travel 36 kilometers upstream. If his boat can travel 16 kilometers in still water, so on a lake or something without a current, what is the average speed of the current on this stretch of river during the rainy season? All right, so we definitely have a rate times time equals distance. And we have two situations here. We have upstream and we have downstream. So upstream, actually they mention downstream first, so we'll go downstream and upstream. Now the question here is, what's the average speed of the current? So the speed of the current, so let x equal the speed of the current. In fact, this one might actually be a little easier than I first thought. We'll see. So let x equal the speed of the current. No, we'll be okay here. So we're looking for that. Pastor Sousa can travel 60 kilometers downstream in the same time it takes to travel 36 kilometers upstream. So let's start with this downstream. Our rate for downstream, he's driving his boat at 16 miles per hour, plus the current is helping him. So this is the new big idea here. For the rate downstream, you're going to take the rate of the boat plus the rate of the current. And that's the main idea here. Other times we won't know the rate of the boat or the rate of the current, and we're actually going to have to add two variables together. But here we know the rate of the boat, we don't know the rate of the current. Our time, as we look through here, it doesn't mention the time at all here, but we see that it's the same time, so we can let t equal our time. That's going to be the same in both. And so we know distance is rate times time, so we can do this t times 16 plus x. And then upstream you're going against the current, so the regular boat speed minus x. Our time is still t, and we have t times 16 minus x. Now, we have these two things, and we know a little bit about this distance here. So here's our distance because it's rate times time, but also for downstream, we know our rate is our distance is 60 kilometers. So this distance, the first distance, downstream, t times 16 plus x equals 60, and the rate, or upstream, the distance, which is t 16 minus x, is equal to the distance upstream is 36. So we have these two equations. If we have two equations with two variables, we should be able to solve it. So let's distribute our t here. We get 16t plus, and this is kind of interesting, we have t times x, so tx equals 60. And then down here, we have 16t. Distribute the t, we have minus tx equals 36. And at first that might look a little scary, but in fact we actually have the same term here. We have a 1tx, or opposite terms I should say, a 1tx and a negative 1tx. So this is set up very nicely for elimination right off the bat. So we can add these. 16t plus 16t is 32t. tx minus tx is 0. They eliminate. Equals 60 plus 36 is 96. Divide both sides by t. I said that wrong. Divide both sides by 32. 96 divided by 32 is 3. So t is 3. Well, back here, that's time. We were talking about kilometers per hour, so our time is 3 hours. Great, we found the time, but actually, it didn't even ask for the time. It might be helpful, but its time is 3 hours. We want to find the average speed of the current, which was x. So what we can do is we can go back into one of these equations and figure out what x is equal to. So let's take this top one here. So we're going to use this. We know our time is 3. The rate was 16 plus x equals 60. We can distribute. 3 times 16 is 48 plus 3x equals 60. We subtract 48 from both sides, and we get 3x equals 12. Dividing both sides by 3, x equals 4. And we are dealing with kilometers per hour for our rate, so 4 kilometers per hour. And so that is the rate of the current. Again, the big idea is when you're going downstream, you're going to take the rate of your boat, plus the current. Run out of room here, so rate of boat plus the rate of the current, and here it's minus the current. And again, there's going to be similar things with planes where a tailwind is going to be plane plus airspeed or current, and headwind would be plane speed minus current or airspeed.